quickly recap what we learned yesterday about the moment of inertia. So moment of inertia is basically like a rotational mass when we talk about things rotating about some axis. Now, really, when we talk about moment of inertia, an object that has a large moment of inertia means it does not want to move very easily, does not want to rotate very easily. So objects with a low moment of inertia are easily accelerated, whereas objects with a larger moment of inertia take a lot more torque to accelerate those objects. So using what we learned yesterday about moment of inertia, we're going to go ahead and try to calculate the example at the bottom of this page in your notes. So I would recommend, if you have a sheet of paper, if you have a hard copy of the notes, you could do it on there, or maybe write this on a separate sheet of paper so you could later transfer it out onto your iPad notes. So in this example, we have a rod of mass 4 kilograms and length 2 meters, and it's free to rotate about an axis through its center. A 3 kilogram sphere of radius 0.25 meters is added to one end of the rod. What is the moment of inertia for the body? Now, if we look up at the chart here to see the different moments of inertia, we can see that different objects have different moments of inertia. But just like we did with center of mass, when we have a system that has multiple bodies, we kind of have to do the same thing as we do for center of mass, where we add the all the masses times their position together to find that center of mass. Same thing with inertia. So I'm going to take the moment of inertia, we'll call it system for the system, and that's equal to the moment of inertia for the rod plus the moment of inertia for the sphere. Okay. So the moment of inertia for the system is equal to the moment of inertia for the rod. So now we got to go back to our chart here and see what is the moment of inertia for a rod rotating about its center of mass. So if we look here, rod about center of mass, that's 1 over 12 ml squared. So we scroll back down to the problem and we go ahead and plug in those values. So we got 1 over 12 times the mass of the rod, 4 kilograms, times its total length squared, so 2 squared. So that's the moment of inertia for the rod. Now for the sphere, if we look back up top here, we can see that there's a couple moment of inertia equations for the sphere. However, if you guys notice, these moment of inertias, these have to do with a sphere rotating about an axis through the sphere itself. If we go back into this problem, this sphere on the end of this rod is not being rotated about an axis through the sphere. It's away from the sphere. So really we got to think about this sphere, this 0.5 meter diameter sphere, as being like a point mass. So if you look back to the notes from yesterday on the first page, that generic equation I equals mr squared, that's really what we're using, since this axis is not through the sphere itself, so it's like a point mass. So the equation for that is just mr squared, so the mass is 3 kilograms for the sphere times the radius squared. Now the radius is the distance from the axis to the center of the sphere, kind of like gravitation, where we use the distance between two planets being the distances from their center. Same sort of thing here. So the length, or half the length really, so 1 meter, plus the additional radius, 0.25 meters. And we go ahead and square that, and we can get our answer from here. So when we go ahead and do our math, we can see that the total moment of inertia for the system is 6.602 kilogram meters squared. That's the units for moment of inertia. Now, thinking about this kind of conceptually, again, we want, if we want to rotate something easily, we want a small moment of inertia. Anytime we add objects, masses, especially far away from our axis of rotation, it's going to increase that total moment of inertia, which is going to make it that much harder to rotate. So without a doubt, this particular system is a lot harder to rotate than the system would be if the sphere was non-existent. If it was just the rod itself, that would be able to rotate very freely, and that ultimately has to do with the fact that the center of mass of the system is actually far away from the axis. So the center of mass of the system, we can probably kind of estimate, would give or take probably be in this area around here. Right, it's far away from the axis. The further away it is from the axis, the larger the moment of inertia, the harder it is to rotate. Unit 7 is virtually all, or most of Semester 1 wrapped up into objects spinning or rotating. Therefore, there isn't anything new, just a bunch of old stuff written in different ways to describe rotational motion instead of linear motion. So if we go ahead and look at this chart, now it may look a little overwhelming at first because there is a lot of stuff. There's a bunch of new variables that we have to look at. All of these look extremely new to you with the exception of torque, since we've already talked about that, and moment of inertia, but everything else is pretty new. Now, don't panic about this because really when you look at this, you're going to see a lot of similarities between these new terminology, these new variables that we have. There's a lot of relationships between them and things we've done with linear motion. So I want you to go ahead and pause this video for a couple minutes and literally just study. So look at the rotational terminology with their variable and then look at the linear motion equivalent. So go ahead, pause this video for a couple minutes, and then play once you're ready. Alright, so hopefully you got a chance to kind of study this a little bit. So let's talk through these different terms, because they are going to be important to us going forward. So let's talk about angular displacement first. In linear motion, we've all heard of displacement. Displacement is simply just delta x, so it's a change in position. Well, it's no different when we talk about rotation. The term angular literally stems from the word angle, right? So when we talk about something spinning, if something spins one rotation, makes one revolution, we got to think really of the unit circle. So we're going to kind of bring the unit circle into this a little bit. Now you don't need to know the trig identities, you know, cosine, sine, all that stuff too much, but you definitely need to know that one revolution is 2 pi, for example, or maybe a quarter of a revolution, 90 degrees, is pi over 2. So that is going to kind of help us out a little bit. So angular displacement is theta angle, so again, something like 1 revolution, that's 2 pi radians, and that's measured in radians. Okay, and when we look at the equation with the variable inside of it, this equation, although it has new variables in it, really looking at it, it's not that different from one that we already know. If you think back to Unit 1 with kinematics, delta theta in this case is basically your delta x equals omega naught. We're going to talk about omega, but that's basically a velocity times time, plus 1/2 your alpha is basically your acceleration, t squared. So this is an example of an equation that we have for angular displacement if we're possibly trying to find that. So again, it's just how many radians something covers. As opposed to meters, it's radians now. When we look at angular velocity, again, very similar to linear velocity. Okay, now the only difference really, if we look at the units here, radians per second. Now we know linear velocity is meters per second, so how many meters you traveled in a second. Well, it's the same is true for angular velocity, except it's radians. So what was your theta? What was your angle in radians? Not degrees, unfortunately, but radians per second. Right, so if it takes me, let's say 2 seconds to make one rotation, so essentially a period of 2 seconds for something spinning in a circle or rotating, okay, that's 2 pi radians over 2 seconds, giving us an angular velocity of pi radians per second. So again, it's just how fast, but really how much angle, how many radians are covered in 1 second. So it has to do with the speed. Now, when we think about, really tie this to tangential velocity when we talk about circular motion, if we have something spinning in a circle, and if we have 2 points on that circle, one, let's say, is a little bit closer to the center and the other is further out, we learned in the last unit that the object that is further away from the center is going to be moving faster, right, because that radius is larger. With angular velocity, it doesn't matter how far the object is from the center of the circle. The angular velocity is going to be the same, because however long it takes to go around, it's going to cover the same amount of radius, doesn't matter how far it is from the center. So that's just something to think about, and if that confuses you, just hold off and we'll talk about it more in the next coming days, but that's essentially what it is. Angular acceleration, again, kind of similar to angular velocity, but it's the radians per second squared. So the equivalent of that, the linear equivalent, is your A, is your meters per second. So essentially, how many radians per second are you speeding up? So there's, again, a couple equations for us here. And if we look at this equation right here, I want to talk real briefly about this equation right here. Looks kind of interesting, looks kind of new, we haven't really seen this before, but really if we think about the linear equivalent, we know acceleration is basically like your alpha, so you could think about this as your A, so we'll go ahead and write that. So A equals torque. We've already mentioned, torque is essentially a rotational force, so that's F, over, and we talked about I, moment of inertia. Moment of inertia is kind of the equivalent of mass. And we essentially derived here, kind of see a relationship there. We came up with Newton's second law. F equals ma, just obviously rearranged, solving for acceleration. So hopefully you're starting to see some similarities. Next we have torque, again pretty self-explanatory. We've talked about it before as well, so it's a rotational force. You guys already know that torque is radius times force. Radius and force are perpendicular to each other, so no surprises there. Moment of inertia we've already talked about as well, labeled I, measured in kilogram meters squared. Right, so the moment of inertia is basically rotational mass. Now this is the general equation, kind of from previously, if you look on the previous couple pages with the notes, mr squared. Now again, it's the sum of mr squared. We didn't write that on the previous page, but like we saw in the previous example that we did, if we have a two-body system or a three-body system, to find the moment of inertia for that system, we have to add up the moment of inertia for each system. Now the nice thing with this, because of this summation, we can kind of see that, is it's not a vector quantity, so it's not plus or minus. You're always adding up moments of inertia. The more objects you add to a system, it's going to make it harder and harder to rotate. Just like when you increase the mass of something, it makes it harder to accelerate it. You need a larger force. Same is true here. Add more mass, add more objects away from the axis, right? That increases the moment of inertia. Next, we look at angular momentum. You guys already know what momentum is, but now angular, when something rotates, it's got angular momentum. Now, there's actually a lot of cool demos with angular momentum, which we'll show you guys in the next few days here. But angular momentum is actually labeled with the letter L, okay, and it's measured in kilogram meters squared per second. Kilogram meters squared per second. So it's really your mass times your momentum vector. So you go ahead and have those units. Now again, the equivalent, you probably guessed, is momentum, linear momentum with lowercase p. Here's a couple equations for us. You guys already know what the other variables mean. I, moment of inertia. We got omega, the Greek letter omega, which is the angular velocity. Right, so that's essentially your mass times your velocity if we think about it in terms of linear motion. So it should make sense there. All these equations are on your equation sheet, so there are no surprises at all. Finally, we have rotational kinetic energy. Now, this one's interesting, and I want you guys to think for a second about this. If you think back to the energy unit, Unit 4, when we talked about energy and we did conservation of energy and things rolling down a hill or something along those lines, if you guys remember, all those problems that we did all had masses that were pretty much sliding, whether it's a box or a sled or whatever it was always sliding. We never had anything rolling, and that's for a reason. Because when something rolls, like a ball or maybe a cylinder, like we did a demo of the other day in class, right? There's rotational, now kinetic energy. So that doesn't mean that all of a sudden 1/2 mv squared doesn't exist. It absolutely does. 1/2